Good morning. My name is Grant DuBois. I'm with a Thailand-based manufacturer of stevia sweeteners known as Almendra. And this morning, I'd like to share with you some work I've been doing with Almendra over the last few years. I am an organic chemist by background, but a biologically oriented organic chemist that's always tried to understand the physiological mechanisms that were responsible for the unusual tastes of different taste stimuli. Before joining Almendra, I was with the Coca-Cola company for about 20 years, where I was responsible for new sweetener technology development. And at the Coca-Cola company, we were the first to initiate and successfully establish as GRAS a stevia sweetener for use in the US market. And in addition to that, while at the Coca-Cola company, I initiated the program with Genomics to find the first positive allosteric modulators or enhancers of the sweetener receptors, so that we could make carbohydrate sweeteners more potent than they are. Prior to joining the Coca-Cola company, I was with the NutraSweet company, where I was responsible for new sweetener research and development. By way of outline of what I'm going to talk about today, first I want to talk about metrics for commercial viability. I've seen so many programs over the years where people have spent a lot of money developing a sweetener technology and it didn't meet the metrics adequately, and so the commercial success just was not there. After that, I'll talk briefly about the history of innovation in the sweetness technology field, where I'll talk about synthetic non-caloric sweeteners. I'll talk very briefly about sweetener receptor enhancers or positive allosteric modulators and natural non-caloric sweeteners. Then I'll move into the main body of my presentation, which has to do with sweetener taste modulation, and finally conclude with a little information on umami taste modulation. So let's talk about metrics for commercial viability first. First of all, a new technology has to be safe, or it won't be approved by regulatory agencies. It has to have adequate taste quality, and I listed here 4 times because, number one, it's really important. If you don't have good taste quality, you don't have a product. And second, because over the years we developed 4 different sensory techniques for quantifying different aspects of taste quality, and I'll share that with you. And of course, it must be sufficiently stable to hydrolytic conditions and sunlight. It must be sufficiently soluble and have rapid dissolution in water. It must be cost effective so it can compete with other technologies. It must be patentable. If you're going to spend tens of millions of dollars on commercially developing a technology, you want a period of exclusivity. And finally, must be acceptable to consumers. And here I'm talking mainly about the GMO issue. I wrote a review a few years ago covering these metrics, and the reference is given here. So let's first talk about these metrics for taste quality. The first one I want to discuss with you is maximal response. So here's some data for saccharin. And on the y-axis of this plot, I show sweetness intensity in sucrose equivalent units. So 10 means equivalent to 10% sucrose. And on the x-axis, I show units of concentration for saccharin. And you can see that the sweetness intensity of saccharin does not go up linearly with concentration. In fact, it's hyperbolic. And this hyperbolic relationship is well modeled by the law of mass action, and don't be too concerned about that, but I want to draw your attention to the number in red, 9.1. This means that the sweetness of saccharin will asymptotically approach that of 9.1% sucrose. In other words, you can't get to 10% sucrose with saccharin, at least in a citrate buffer. Next is some data on cyclamate, and you can see with cyclamate, it has a much higher maximal response, reaching about 18% sucrose equivalent. And with aspartame, we can get up to about 25% sucrose equivalency, which is why aspartame can be used alone as a sweetener. It does not have to be blended with other sweeteners. And finally, here's some concentration response function data for Rebaudioside A, or REBA as I often call it. And you can see we have a problem. It seems that we have a problem similar to what we have with saccharin, in that the maximal response is less than 10% sucrose equivalency. That's not quite the case, and as I'll show you later in our taste modulator work, we've been able to substantially solve that problem for stevia sweeteners and Rebaudioside A. And this work is work that was done at the Coca-Cola Company, has been previously published. Okay, flavor profile. I show here the flavor profile of 6 different sweeteners, and you'll see on the left we have sucrose, and, and sucrose only has sweetness. But when you get to saccharin, we have a fair amount of bitter off taste. Now you'll notice that all of these sweeteners data have been normalized so that they have the same maximal sweetness intensity. So to get to a 7% sucrose level of sweetness with saccharin, you get a lot of bitter off taste. And you can see for the rest of these sweeteners here. And with Rebaudioside A, we have a lot of a licorice-like off taste. But this is with the Rebaudioside A that we were commercially developing when I was with the Coca-Cola Company, which had a minimum spec of 97% Reb A. The ultra pure Rebaudioside A that is a commercial product of Almendra does not have these off taste problems and is really quite clean in taste. And this data has also been published previously. The next taste quality metric I want to talk about is temporal profile. This is the major problem with non-caloric sweeteners, whether they be synthetic or natural. And here I show some data for 6 sweeteners where, again, I've normalized the data so that the maximal sweetness is all 7% sucrose equivalency. This ensures we're comparing apples with apples and not apples and oranges. And you can see that the sweetness of sucrose rises rapidly and it drops off rapidly. Cyclamate is similar, but cyclamate is no longer approved in the US. But sweeteners like aspartame, while it also rises relatively quickly, it lingers considerably compared to sucrose. And then Rebaudioside A lingers even longer. And with Rebaudioside A, you can even discern some delay in onset of sweetness. And then the protein sweetener thaumatin, marked delay in onset, and then long sweetness linger. This is the major problem to solve in making non-caloric sweeteners taste more like sugar. The final taste quality metric has to do with a phenomenon I call sweetness desensitization. And this is some old data from my time with the NutraSweet company, where we're comparing 3 different colas, and what the panelists are doing are tasting the cola iteratively every 30 seconds. And so the top one is sweetened with high fructose corn syrup, and the sweetness at 0 time does not decrease as we go out to 30 seconds, 60 seconds, and so forth. On the other hand, the product with aspartame actually drops off over time. So aspartame is causing some desensitization of the system. This sweetener I've just alluded to, or abbreviated as CPU, actually dropped off much more than aspartame. And actually, I was one of the panelists in this study. And for me, the third taste at 60 seconds, it was almost not sweet at all. So a desensitization is also something that can happen with sweeteners. Okay, the next metric I want to bring to your attention is cost. And cost, and the way I'm going to talk about it is focused for the beverage industry, for 0 calorie, well, for the beverage industry. And here's a table with costs, and I want to draw your attention to the numbers in the oval here on the right. And here is, for example, the US Coca-Cola Classic. If it was sweetened with high fructose corn syrup, and I've used internet pricing here, if it was sweetened with high fructose corn syrup, it'd be about 54 cents. as far as the cost per unit case of Coca-Cola. On the other hand, if it was sweetened with cola beverage sweetened with a mixture of saccharin and aspartame, which is what Diet Coke was in the early 80s, it would be around 12 cents. In the mid 80s, because saccharin containing products were forced to carry a cancer warning label, companies wanted to get that warning label off, and so there was interest in going to 100% aspartame product, which happened in 1985. And the price came down from the NutraSweet company down to around 110 a kilo, but the cost was somewhere around 32 cents. Today, aspartame is a generic product. It's off patent, and the cost of sweetening with aspartame is very low. On the other hand, sweetening with Rebaudioside A, if we were to use Almendra's ultra pure REBA product at its list price of 120 a kilo, we're around 34 cents. But this product doesn't taste good enough. It has some taste problems. We found we could fix the taste problems if we blended the Rebaudioside A with erythritol, but now the cost is up to 90 cents per unit case, which is way too high. So the key point here is there's great need for a cost-effective taste modulator for Rebaudioside A. Okay, that's all I'm going to say about metrics. Let's talk quickly about the history of innovation in the sweetness technology area. First of all, what the consumer really wants is the taste of sugar. And chemists like me have been synthesizing and synthesizing and synthesizing thousands of new molecules, trying to find high potency sweeteners that would taste just like sugar. And as close as chemists have come is with molecules like aspartame and sucralose, which taste pretty good, but still, they're not going to fool anybody. In the in the early 2000s, after the human sweetener receptor was cloned by Genomics, it became possible to screen for positive allosteric modulators or enhancers of the sweetener receptor. And we hoped that we would be able to find 10-fold, 20-fold enhancers of sucrose taste so that we could get the calories way down. But since we're keeping the sweetener the same, we thought it would still taste like sugar. Well, that turned out to be true, except the most efficacious enhancers we could find were about 2-fold enhancers. So you could only get a 50% calorie reduction. And in addition, these are all synthetic molecules, and they would have to be labeled as artificial flavors. So it wasn't much of a commercial success. Also around 2000, while I was with Coca-Cola, marketing became intensely interested in getting all of their ingredients to be natural ingredients, including sweeteners. And so I was asked to focus on finding the best natural non-caloric sweeteners. And at that time, considering metrics for commercial viability, the best option as a result of my research was Rebaudioside A, a stevia sweetener. However, as you can see by my drawing, the taste is still quite a ways away from the taste of sugar, farther than the better synthetic sweeteners. And so none of them were useful by themselves. This led to our work around the same time to find modulators of sweet taste that would bring it much more closely to the taste of sugar. A little bit about Rebaudioside A, which I often just refer to as REBA, grows in fields like this. The sweetener is in the leaves of this Stevia rebaudiana plant. Chemists like me might draw the chemical structure of Rebaudioside A like this. This is the hydrocarbon backbone, and these are carbohydrates. I draw it this way because all the glucoses are in the same orientation, and you can see that they're glucoses easily. A better way to look at the structure is like this in a three-dimensional drawing, where you can see the hydrocarbon backbone and the glucose is all on one side, or as a space filling model, it's even better. You can see that the hydrocarbon backbone is like this and the sugars are on the other side. Okay, back to metrics for commercial viability again. talked about safety, and these are the taste quality problems that we need to solve by formulation if we're going to make REBA taste better. These are the other metrics, and I'm not going to worry about them, but these are my challenge. This was my challenge over the last years in my work with Almendra. Okay, sweetener taste modulation. As we began to think about it, and as I began to think about what causes this sweetness linger, this low sweetness intensity, this slow sweetness onset, this sweetness linger, sweetness desensitization, what are the mechanisms of this? Well, there were a number of empirical observations made over the years. One of the early ones was that ordinary salt, sodium chloride, increases the potencies of stevia sweeteners. We found that we could replicate this, but actually what's going on is the sodium chloride accelerates the sweetness onset rate and the and cuts the sweetness linger, and really makes the potency seem higher. Later work was found by one of my colleagues at the NutraSweet company that ordinary salt can eliminate the sweetness linger of aspartame. Then we began work at when I came to Coke, and we found that it's not unique to sodium chloride. Potassium chloride also reduces the sweetness linger of aspartame, and potassium chloride works just as well. And they also add mouthfeel. We also observed in this early work that aspartame in tea has negligible linger. We also found that when we began working with stevia sweeteners, that pretty much any osmolytes, including erythritol or these salts, eliminate REBA sweetness linger. Then as I began work in this field for Almendra, we made the observation that you could rinse your mouth with any astringent solution like alum or tannic acid and so forth, and it would increase the apparent sweetness intensity, accelerate sweetness onset rate, and cut the sweetness linger of REBA. And another final observation, we found that if you tasted the REBA solution the first thing in the morning when you just get up without rinsing your mouth or anything, it would have very low sweetness intensity, very marked delay in sweetness onset, and very pronounced sweetness linger. Well, all these observations led us to the hypothesis that this has something to do with the mucus in the mouth. All of these negative taste attributes of REBA and aspartame and other non-caloric sweeteners has something to do with the mucus in the mouth. And it led us to a hypothesis, mechanistic rationale, and this is a key thing that I want to communicate with you. I'm sure that you understand that out in the literature and from many different suppliers, many people claim to have taste modulators of the negative taste attributes of natural sweeteners and so forth, bitterness inhibitors, substances that add mouthfeel and so forth. Well, I think we understand now the mechanism of these effects, and that's led us to some very unique formulations that dramatically improve the taste of sweeteners. So what we came to realize is that the low sweetness intensity, delayed sweetness onset, sweetness linger, these have to do with the mucus hydrogel that covers the tongue where your taste buds are located. This mucus, the structural basis of it is a glycoprotein called mucin. And this mucus is secreted by salivary gland cells. Mucin, the glycoprotein in mucus that forms this hydrogel, is normally maintained in a very compact state in the salivary gland, bound to calcium. However, when it's secreted as saliva, the calcium is retained in the salivary gland cells, and the mucin comes out and spreads out and forms this gel-like film over your tongue, which is the slippery surface on your tongue. Obviously, sweet molecules have to diffuse through this gel in order to get to the sweetener receptor on your taste buds. And it occurred to us that while carbohydrate sweeteners diffuse right through this gel very, very rapidly, non-caloric sweeteners do not. They bind to the mucin on the way through. They bind to hydrophobic sites in the mucin on the way in, which is why they're slower in onset in many cases. And then in diffusing away from the receptor, they have to go back through the mucus layer, and they bind to the mucin over, and they return to the receptor over and over and over and activate it over and over. And that's what causes this sweetness linger. Well, here's some reference information on saliva and its role in taste, and a reference to some work by the Professor REBA's laboratory at MIT, where she has been studying the effect of mucus on the delay in absorption of drug molecules through the mucus in the gastrointestinal tract. Well, I already mentioned to you that a factor in this mucus layer is mucin that forms this hydrogel, and that mucin is maintained in a compact form in salivary gland cells when it's bound to calcium. Well, that suggested that, gee, what if we just formulated a sweetener like REBA, the stevia sweetener REBA, with calcium salt. Calcium may then bind to the mucus, to the mucin in the hydrogel, and cause it to shrink, and allowing rapid diffusion to and from the receptor and solve the problem. And we began to experiment with that, and I'm going to tell you more about that in a minute. But as we started experimenting with calcium salts, we noticed that these calcium salts also introduced a marked mouthfeel increase. And it turns out there's some work published by Japanese workers a few years ago where the calcium sensing receptor, which has been extensively studied for its role in maintaining blood calcium levels, it's also expressed in a subset of taste bud cells, and when it is activated, it leads to a perception of sugar-like mouthfeel, which has been referred to by the Japanese as kokumi taste. And there are some references to that. Well, it turns out that magnesium also activates the calcium sensing receptor, not just calcium, and also that both sodium and potassium ion act as enhancers of the activity of magnesium and calcium at the calcium sensing receptor. And so, long story short, eventually we came to blends of potassium salts, magnesium salts, and calcium salts as the preferred compositions for modulating the taste of Rhodiocyte A. And here's some data in a citric acid buffer system. And first, I'd like to draw your attention to the fact that when we look at sweetness intensity, this is 10% sucrose. And when we're looking at Rhodiocyte A by itself, the sweetness at 500 ppm, the sweetness intensity is low. If we just add potassium chloride, no effect. No effect with magnesium chloride, no effect with calcium chloride. But with the mixture of all three, now we see an increase in sweetness. We also see a very nice effect on mouthfeel. Again, here's the mouthfeel of 10% sucrose, mouthfeel of the Rhodiocyte A alone sample, and with the individual minerals by themselves, basically no change. But when we have the three all together, we see a dramatic increase in mouthfeel. Similarly, with sweetness linger, we don't see any effect, really. There's no sweetness linger for sucrose. REBA, a lot of sweetness linger. And the three minerals by themselves at low concentrations, no effect. But when we have them all together, we drop the sweetness linger roughly in half. So the key point here is that these mineral salts are synergistic with each other in enhancement of sweetness, accelerating sweetness onset, reducing sweetness linger, and addition of mouthfeel. Well, one question that occurred to us is it necessary that all of these salts be chloride salts, as in the last slide? because sensitive subjects with all chloride salts found that these samples were salty in taste. So this is some work that we did with another blend where only the potassium salt was a chloride salt, and we looked at its effect on rebodioside A in a lactic acid buffer system. And here, again, I'll draw your attention to the effect on mouthfeel. Here's the mouthfeel of 10% sucrose, and here's the mouthfeel of REBA alone, essentially nothing. And when we added the taste modulator at 2 different levels, we saw a dramatic increase. And similarly, here's the sweetness slinger of sucrose, nothing. The sweetness slinger of the REBA sample, quite significant. And with the taste modulator at 2 different levels, reduced to less than half. So key point here is that the taste modulator activity of the mineral salt composition is independent of anion composition. Okay, I'm sure many of you have heard about claims that rebodioside D and rebodioside M are claimed to taste better than rebodioside A. And so we wondered whether if we formulate rebodioside A with mineral salt composition, would it taste better than rebodioside D and rebodioside M? And here's some data on that type of experiment. And I'll draw your attention first to mouthfeel. Here's mouthfeel of 10% sucrose, rebodioside A, rebodioside D, rebodioside M, nothing really. And here with 2 different levels of the taste modulator, in this case an all chloride system. Dramatic increase in mouthfeel, more than that of the sucrose solution. And similarly, reduction in sweetness linger, rebodioside A sweetness linger, D and M, and then significant decrease in sweetness linger with the REBA, with the taste modulator systems. So the key point here is that the taste quality of rebodioside A formulated with the taste modulator is superior to that of REB-M. You'll notice there's a little bit of salty taste here that was picked up by some panelists, and however, this was early work, and I'm confident that if this was a sulfate salt, and if this was, for example, lactate salt, we would not see that effect. Okay, we also wondered if we couldn't just take commercial products like an all aspartame sweetened cola and spike the taste modulator and make it taste better, and here's some data on that. And I'll draw your attention first to mouthfeel. The mouthfeel of the cola without taste modulator is basically 0, but with the taste modulator, this taste modulator up to a level comparable to or a little better than that of 10% sucrose, and sweetness linger reduced, again, almost eliminated. So the key point here is that the taste modulator can dramatically improve the taste quality of beverages sweetened with aspartame or other synthetic sweeteners. We also looked at the taste modulator spiked into mid-calorie products, in this case a commercial mid-calorie sparkling lemonade sweetened with REBA and sucrose. And here's some data, and again I'll draw your attention to mouthfeel. And here's the mouthfeel for the product with 5% sucrose and the rest of the sweetness from REBA, but when we add the taste modulator, we can get dramatic increases in the mouthfeel. Key point here is that the taste modulator composition can dramatically improve the sugar-like mouthfeel of mid-calorie beverages. We even wondered whether the taste modulator might even lead to improvement of a full-calorie beverage prototype. And here's some data of a sucrose beverage prototype. And again, I'll draw your attention to mouthfeel. Without the taste modulator, the sucrose mouthfeel was significant as expected. But when we added the taste modulator, we could get a doubling of the mouthfeel effect. You might wonder what this tastes like. Actually, it tastes just very good. So the key point here is that the taste modulator can dramatically improve the sugar-like mouthfeel of full-calorie beverages as well. Okay, back to costs. I said that any new sweetener modulation system that we are to come up with has to be cost effective. And I'm showing you the table here. And again, I'll draw your attention to the numbers in the oval on the right. You've seen everything in this table above 90.3 here before. And so if we were to formulate a beverage with Rebaudioside A, with Almendra's ultra pure Rebaudioside A, which is at 120 a kilo, and the taste modulator at 1,000 ppm, we're at around 43 cents a unit case. And if we go higher, 2,000. Something I'm not able to talk about today is Almendra has agricultural technology in development where we expect to be able to make our ultra pure Reb A available at $50 a kilo. When that is the case, putting it together with the taste modulator, and this is a pre-commercialization price of 15 a kilo for the taste modulator, somewhere in the 24 to 31 cents per unit case range. So key point, the potassium, magnesium, calcium, mineral salt taste modulators really enable formulation of all natural sweetener system, 0-calorie beverages with taste qualities comparable to synthetic sweetener system beverages and with acceptable costs. Okay, the last thing I want to talk about briefly is the effect of this taste modulator composition with MSG, monosodium glutamate, the prototypical umami taste composition. And here I show you some data, and I'll draw your attention to mouthfeel again. Monosodium glutamate has salty taste as well as umami taste, but by using this taste modulator, we can dramatically increase the mouthfeel. And it really is a pleasant taste that you observe. And this is a demonstration that we're going to show to you so that you'll be able to observe this effect. So the key point here is dramatically improves the mouthfeel of umami formulations. So now is the demonstration. And here, you should have received 2 samples in the mail from my colleague. And one is an MSG solution in distilled water, and the other is the same sample, but with the taste modulator. And what I'd like you to do is taste the MSG control first, followed by the MSG with the taste modulator. Generally with this procedure, first rinse your mouth gently, not too vigorously, with about a half an ounce of water and swallow. Then take about a half an ounce of the sample into the mouth and swish around gently for about 15 seconds, scaling or forming a mental image of umami intensity, saltiness intensity, and mouthfeel intensity on a 0 to 15 scale. You can write those down. I've memorized a 0 to 15 scale for sucrose being the calibration standard, and if you want to write them down, that would be good. Then after 15 seconds, rinse with a half an ounce of water with gentle agitation and swallow. Then wait a minimum of 2 minutes and repeat with the MSG sample with the taste modulator. And that's it as far as tasting those materials. What I would like you to do is do this as I finish my remarks. I also like to share with you the effects that we've seen when we've just used this taste modulator added to a commercial umami seasoning, in this case paired with mushrooms, onion, mustard, and pepper. And what we see is this kind of effect where again we see this marked increase in mouthfeel of the composition. And so the key point is this taste modulator can significantly improve the mouthfeel of umami seasonings. We also looked at adding the taste modulator to a hydrolyzed vegetable protein system, in this case a pea protein. And again, I'll draw your attention to mouthfeel. The the hydrolyzed vegetable protein system really didn't have any significant taste, but when we added the mineral salt composition, a very nice increase in mouthfeel of the system. So, last, I'd like to summarize what I've told you. And first of all, for non-caloric sweetener formulations, whether it be aspartame or sucralose or stevia sweeteners or bodiacide A or any sweetener, we see sweetness enhancement, we see accelerated sweetness onset, we see reduced or attenuated sweetness linger, and we see increased mouthfeel. If we look at the taste modulator mid or full calorie sweetener formulations, we see sugar-like mouthfeel. And finally, if we look at it in umami formulations, we see increased savory mouthfeel. Most of what I've told you is covered in a patent, a US patent that issued to Almendra earlier this year. And finally, I'd like to say if people are interested in samples, please contact my colleagues Rajesh or Eric. And if you have technical questions, you may contact me by email. And thank you for your attention.